there are, so, but traditionally, like we said, only the server was considered to be adversarial. So the answers were not trusted because they were generated by the server. So additionally, a proof had to be returned with the answer. But in this setting, we are also considering leakage from the proofs, which means that we are also saying the client can be adversarial and trying to learn more information than the answer itself. So we want the answers to be simulatable given only the answer and nothing else. Okay, so I'm directly going to model the security properties. The first property is the soundness, and this is as you would expect. This is for the adversarial server. So you see that in the initial setup phase, the adversarial server receives the public key from the challenger, and later it comes up with a set of its choice after looking at the public key. And as a response, it gets back those digests, like you saw. This is the so the digest is this public digest that the owner publishes, the purple box and the orange box. So it gets back the digests, and later it can adaptively ask for update queries, and it will get the corresponding updated digests as a response. And finally, it comes up with an index J and a query and an answer and a proof, and we say that it is able to forge it if the answer was not correct with respect to the query on database Chi-J, on the set Chi-J, but the proof was accepted. And this should happen with negligible probability. Meaning, let's say in the set Chi-J, X was not an element, but the server was able to prove that, the adversary was able to prove that it was an element. Then that's an accepted forgery. So this is as you would expect. This is a sound definition. And then we formally define zero knowledge using simulation-based definition. So this actually models the adversarial behavior of the client, who might try to learn more information than the answer itself from the proof of the answer. So in this setup, the adversary receives the public key from the owner as before. Then it comes up with the set Chi0 of his choice, which is sent to the real challenger. But the simulator gets no information of this set whatsoever, except that a notification that the adversary has committed to a set. And then it gets the client digest as response. So the simulator simulates this digest without knowing the set. And then the adversary can ask two kinds of queries. So the first is normal membership and non-membership query, and the second is an update query. So for the membership and non-membership query, the answer goes, the query goes to the challenger, who comes up with the answer and the proof. But in case of the simulator, the query goes to the simulator, and it is given oracle access to the set, which means it gets only the answer of the query with respect to the set, which is a bit. And then it simulates that proof, and without any other information about the set whatsoever. And for an update query, the simulator only receives a notification that the adversary has updated, without learning what the update is at all. So this actually captures the fact that the update cannot leak any information beyond the fact that an update has occurred. Adversary should not be able to learn anything about it. And then the simulator comes up with the simulated digest. And finally, the adversary has to guess if it is talking to the real challenger or if it is talking to the simulator. And if it guesses correctly, then it wins the game. And we don't want this to happen. This should happen with negligible probability. Okay. So that brings us to the end of the definitions. Now we are going to go into the construction of zero-knowledge accumulators. So if you have any question on the model itself, this is a good time to ask. Okay, so then we go into the construction of zero-knowledge accumulators. S, we will just denote it with S here. Now we are working in the bilinear map setting, where G and G1 are multiplicative subgroups of prime order and pub. Now, to actually set up that, it takes the set X0 as input. It chooses the blinding factor for the set, which is, we denote as R, and it's the sigma 0 of the owner does the update by choosing a fresh randomness R prime, and if an element is to be inserted, then it computes the new digest as the old digest into S plus X into R prime, and if it is to be taken out, it computes it at the old digest into R prime by S plus X. And it gives the new new updated set in its state. And for the server to keep the update information, it keeps its updated record the element that has been inserted or deleted, and additionally keeps this fresh randomness. So everything is constant time here. Okay? So this is the update. And this is basically the zero knowledge accumulator construction, entire construction. So if you can compare it with the Guen construction of bilinear accumulator, which has no privacy, we see that privacy, because of this clever randomization technique, essentially comes for free, except this one operation of witness update, which is a lot more expensive than the Guen's construction, and this is the price we pay for getting privacy. But all the other operations are comparable or exactly the same. Okay. So that brings me to the end of the first, that part of the talk of zero knowledge accumulators. And now I'm going to talk about the union, which is one of the set algebraic operations. And I'm going to show you how we use this technique of zero knowledge accumulator to actually implement set union. Okay, so for set union, first recall what the query is. So the query is, you have a collection of set, chi1 to chi-m, and the client queries return the union of certain indices. For example, so it's easier to understand with a running example. So I'm going to do this running example where the client asks for the union of sets, say 2, 5, and 9. Okay, so the server response is the answer, which is the union of these three sets, along with a proof that it is correct. Okay. So for example, let's say chi2 is A, B, D, chi5 is D and F, and chi9 is A and C. Then the answer in the union should be A, C, B, D, and F. And additionally, the server has to respond to this along with the proof. Okay. So how do I prove that the returned union is correct? So there are two conditions to prove that it is correct. The first is the superset condition, which has to prove that every set is actually a subset of the answer, proper subset or the subset of the answer returned. Now I'm not going to go into the details of this, but given the accumulation, zero knowledge accumulation of each set and the answer itself, proving that this entire set is a subset of the answer is done by the server using a generalization of the set membership technique that we just saw. So the more interesting case for us is to prove that the second condition, which is the membership condition. So this condition means that we have to, the server has to prove that every element in the answer actually came from one of these sets, chi2, chi5, or chi9. Now proving this is more tricky, because even if you use the zero knowledge membership technique, proof technique, this is problematic because it will reveal which set the element had come from. So, but we have to hide that fact also for perfect simulability. So here we devised a new technique, which is to prove that instead, if we prove that the answer is a subset of the multiset union of the set, and if we can prove that without giving out the multiset union of the set, then also we prove membership. So what is multiset union? It is basically the union, but all the elements preserve their multiplicity in this union. Okay. So in our running example, recall that the union was only A, C, B, D, and F, but the multiset union have two A's, two C's, and so on. So it actually preserves the multiplicity. So now the server has to first prove that it has computed the sigma of multiset union, accumulation of the multiset union correctly, and then prove that the answer is a subset of this. Now the multiset union, so the accumulation of the multiset union, sigma of u tilde, is basically G to the product of the randomness used in the blinding of each of the individual sets into their characteristic equation. So if we expand this, it looks like this. So first the server has to compute that and prove that sigma u tilde is computed correctly, and then prove that the answer is a subset of this. So to prove, to compute and prove, step 1 and step 2, basically the server does the following. So recall that the client has sigma 2, sigma 5, and sigma 9 from the owner itself. These are the blinded zero knowledge accumulations. So the server progressively builds up a tree where each internal node is the multiset union of its two leaves. The server can compute each of these sigma 25, sigma tilde u by using this big string of g to the s up to g to the s to the n that it has. And when it computes this value, the root is basically the sigma of tilde u, which is the multiset union. Now, how will the client verify it? The client gets all these internal nodes from the server, which is sigma 25 and sigma u tilde in this case. So the client can also verify it using bilinear map from ground up. So it has sigma 2, sigma 5, and sigma 9 from the owner, and it builds the root of trust ground up. So it first verifies if sigma 25 is correct using sigma 2 and sigma 5 and G, and then it verifies one level up. So finally it verifies that sigma u tilde is correct. Now once this verification is done, the only thing remains to show is the answer is a subset of this multi-set union, which is also a generalization of the set membership technique in accumulation. So the server computes the witness, which is basically G to the R2, R5, R9 characteristic equation of U divided by the characteristic equation of the answer evaluated at S. So if you expand it, you will find this basically in our running example. And the server can compute this. And the verification will just be whether the bilinear map of the witness and G to the CH of S equals G to the sigma U tilde and G. By now, the client is convinced that the sigma U tilde is computed correctly. Okay. Yeah, so that's basically the crux of how the set union is done. And finally, that brings me to the end of the talk. So more in the paper, specifically in the paper, we rigorously discuss how the zero knowledge accumulator definition and the construction, how this primitive actually relates to the existing primitives of zero knowledge set, primary, secondary, name resolver, trapdoorless accumulator. And then we give a formal proof that this notion is stronger than the indistinguishability-based notion for privacy that was recently considered in these two papers. And finally, we give first efficient construction for the verifiable set algebra using a subset intersection union and difference with almost no additional cost over the existing non-private solution that was proposed in Crypto 2011. And that brings me to the end of the talk. Thank you for your attention.
Thank you. So we have time for a very quick question. Okay, let me ask a question. What assumption do you prove yours?
N bilinear Diffie-Hellman inversion assumption. It's a non-constant assumption.
Okay, yes. So it's related to strong Diffie-Hellman.
Yes.
Yeah, okay. Let's thank the speaker again. So while the speaker sets up, the next talk is about zero-knowledge arguments for matrix vector relations and lattice-based group encryption. And this work is by Benoît Libert, San Ling, Fabrice Muertem, Huang Nguyen, and Hua Xiong Wang. And Hua will give the talk. At 5 minutes, I will tell you. Oh. Can you switch on the microphone?
Hello? Okay, thank you. Okay, thank you, and hello everyone. I'm going to talk about construction of lattice-based group encryption scheme and zero-knowledge arguments necessary for that construction. This is joint work with Benoît Libert, San Lin, Fabrice Muertem, and Hua Xiong Wang. Okay, so first I will recall some background on group encryptions and discuss our difficulties toward realizing lattice-based group encryption. Then I will state our results and describe the techniques that we use to overcome the difficulties. Okay, so let me start with group signatures, which is an important anonymous authentication mechanism proposed by Coleman Van Hess in 1991. In this setting, we have a group of users, and each member can anonymously sign messages on behalf of the whole group. This means that group signature app is hiding the source of the message within a group of registered signers. Group encryption is a primitive introduced by Kyushu and Jung in Asiacrypt 9 years ago. It is an encryption analog of group signatures. Okay, so we have a group of register, receivers, and each sender can encrypt message to an anonymous group members. Okay, so in this way, group encryption aims to hide the destination of the message within register receivers. Another interesting feature of both group signature and group encryption is that the users are kept accountable for their actions. In case of disputes, there is tracing authority and opening authority who has some kind of secret key and who can identify the signer of the message or the receiver of the ciphertext. Okay, so more formally, a group encryption scheme allows encrypting while proving that the following hold. First, the ciphertext is well formed and is intended for some registered group member who will be able to decrypt. Second, the opening authority should be able to identify the receiver should the need arise. And thirdly, the plaintext should satisfy some properties like being a witness for a public relation or being a private key for a given public key. Okay, so this additional requirement is may be useful for spam protection. As pointed out by KTY, some possible applications of the group encryption are in the context of file one filtering for anonymous trusted third parties in cloud storage services. Group encryption also implies hierarchical group signatures, which is a general form of group signatures. Okay, so let me now briefly review some previous work on group encryptions. In the work that introduced group encryption, KTY also provided a modular design that based on ordinary digital signatures, anonymous secure public key encryption, and interactive zero-knowledge proofs. They also demonstrate concrete instantiation based on number theoretic assumptions. Okay, so the KTY schemes only consider the interactive setting, but the scheme can be made non-interactive in the random oracle model via the FASMI heuristic. 2 years later, Catalog et al. Introduced a non-interactive construction that is secure in the standard model under parent-based assumptions. Subsequently, NMNE and Châu suggest various improvements for constructing group encryptions. Okay, and Libet et al. Proposed a refined traceability mechanism that allowed to identify on the ciphertext that intended for specific group members without affecting the anonymity of all of the other members. Okay, so for the time being, on existing realization of group encryption rely on traditional number theoretic assumptions. So usually we don't want to put all of our eggs in the same basket. So it may be worth considering construction from other assumptions, like lattice-based. So lattice-based crypto is interesting, and lattice assumption is still resist against quantum computers. Okay. Okay, so let me move to the context of lattice-based crypto, and in particular, consider lattice-based group signatures. Indeed, it's a very active topic in the last 6 years. The first construction were proposed by Gordon Katz and Vakuntanath in Asiacrypt 10. Since then, various improvements have been made in terms of security, efficiency, and functionality. And the most recent scheme already achieved the logarithmic size in the number of group users and work for dynamic groups, when the first construction only achieved only kind of linear size and only can handle static groups. Okay, so but no lattice-based group encryption so far. So we asked the question, what's the main difficulty here? Okay, so given that both of the primitives can rely on almost the same components, like ordinary signatures, public key encryption, and supporting zero-knowledge proofs. Okay, so in the next, I will describe that the main difficulty lies in the problem of constructing a suitable supporting zero-knowledge proof for group encryption. Okay. Okay, so let's consider the existing zero-knowledge protocols that's used for handling lattice-based relations. In previous work on the protocol in previous previous work can be categorized into two main classes, Schnorr-like and Stern-like. Okay, Schnorr protocols was originally proposed for handling discrete lot relation, but it was then so very useful for lattice relation by Limoges, who introduced the rejection sampling techniques. On the other hand, Stern-like protocol was first proposed in the context of code-based crypto, and it was first considered in the lattice setting by Kawachi, Tanaka, and Sagawa. And then it was empowered by Lin et al. With techniques called decomposition and extension. We observed that the two classes of techniques mainly deal with linear relations, in the sense that equations that contain only terms of the form public matrix multiplying with some secret vector, where the secret vector may satisfy some additional constraint like smallness or have some special arrangement of entries. Okay, so the typical example of the kind of relation is the ISS relation and the LW relation. In the ISS relation, we have an equation A times X equal to U mod Q, where the matrix A and vector U are published, and the secret vector X is small. The LW relation is represented by the equation A times S plus E equal to B, where matrix A and vector B are published. Vector E is small secret noise, and the secret S may be small. Okay, so it also holds this kind of two class also work for encryption scheme based on LWE and signature scheme based on SAS problems. Okay, so now let me go back to the context of lattice-based group signature and see how the techniques work well for group signatures. A modular design for group signature is concise, then encrypt, then prove. It consists of the following. First, each user has a signature sigma on his identity ID, and that signature is issued by the group manager who manages that group. In the process of generating group signatures, then each user is asked to encrypt his identity's ID to a ciphertext C, and that is done using the public key of the opening authority. Then, the signer have to prove in zero knowledge that the following hold. First, he has a secret valid message signature pair with respect to the manager's secret key, public key. That means that he is a certified group member. Second, C is a well-formed ciphertext of ID with respect to the public key of the opening authority. That means that he has done the encryption honestly, and the opening authority can recover ID should the needs arise. Okay, so because of if we use SS-based signature and LWE-based encryption, then the relation underlying the statement can be represented by linear equations, and it can be handled by previous techniques. Okay, so now if we consider the context of lattice-based group encryption, then things become more complicated. Okay, so the modular design by KTY is as follows. Each member has a key pair, SKPK, for an anonymous encryption scheme, and the manager assigns the member's public key PK and publish the pair, PK and the signature sigma. When the sender wants to send something to the group, so a message mu, then he uses PK to encrypt message mu that satisfies some relation R and obtain a ciphertext C. The sender also encrypts the public key PK under the public key of the opening authority and obtain a ciphertext that we call COA. Okay, that's for enabling the opening feature. Then the sender has to prove that the following two parts. First, C is a correct encryption of some message mu with respect to a hidden public key. And second, the sender knows a valid signature sigma on that PK with respect to the public key of the manager, and that COA is a correct encryption of that pk with respect to pkoa. And also the message mu satisfies some relation R. Okay, so we observe that the statement in the second part are similar to the ones appear in the context of lattice-based group signature, and it can be handled with previous technique. The challenging part is essentially the first part, where everything except for the ciphertext is hidden. Okay, so even the public key that the sender used to encrypt the plaintext is hidden. Okay, so if we use some LWA-based encryption for this, then the problem would boil down to proving an LWE relation with hidden but certified matrix. That is of the form x times s plus e equal to b mod q, where this matrix x here is also hidden, but we additionally have to show that we have some signature on it. Okay, so we call this quadratic relation, and we identify this as the main obstacle on our way towards realizing lattice-based group encryption. And overcoming this kind of difficulty likely requires some new ideas. Okay, so now let me state our result and describe the techniques we use. In this work, we introduce a zero-knowledge arguments for quadratic relations. So it's including the relation that I described, where we have matrix X and vector S may satisfy some additional relations. Okay. Our approach is to develop Stern's protocol and to improve its capability from handling only linear to handling quadratic relations. In the process, we propose some new techniques that may be of independent interest. Okay, so once this most difficult part is realized, so we can use it to build the first lattice-based group encryption scheme. The scheme is proven secure in the KTY model under the SIS and the LWE assumptions. Okay, so now let me recall Stern's clever ideas. Okay, Stern's protocol is a zero-knowledge protocol for the syndrome decoding problems, where given public matrix A and public vector U, we have to prove that, okay, we know a secret binary vector X that have fixed Hamming weight W. So Stern did it with two main ideas. First, permuting, which means that to prove the constraint of the witness using random permutation. Specifically, the prover send the verifier a permutic vector pi of x. Okay, so we observe that the following equivalence holds. Vector x has the constraint binary vector with weight w if and only if pi of x does. Okay, so if the verifier sees that pi of x has this constraint, he should be convinced that x is a valid witness. And moreover, because pi is random, it completely protects the actual value of x from the verifier's view. The second idea is masking. That means to prove the linear equation using a random masking vector r. Specifically, we send the verifier with the y that equal to s plus r, and show him instead that a times y equal to u plus a times r, which is sufficient to convince the verifier that the original equation a times x plus equal to u holds. Okay, so let's go back to our quadratic relation. We will employ a two-step solution. In the first step, we will pre-process the given quadratic relation so that we obtain a somewhat more familiar form. Second, we will exploit Stern's ideas, especially the permuting idea, where we will set up some kind of permutation that leads to a similar equivalence like the above, and then exploit the random permutation. Okay, so in the first step, we transform the term matrix X times vector H into the form of public matrix times a secret vector. To this end, we do the following. First, we write this one as the sum up on of the product Xi, Si, where the xi are the columns of matrix X and the si are the entries of vector S. Okay, so all of them are elements of the Q. Second, we look at each of the term xi times si and use a decomposition matrix to break all of the entries of vector X into binary. And we obtain an equation that xi times si equal to that public matrix multiplied with a vector whose entries are xij times si, where xij are binary and si are still element of the Q. Next, for each of these terms, xij times si, we do the same decomposition process and obtain the form that, okay, so it can be represented as a public vector multiplied with a binary secret vector. So combining all of these substeps, we will obtain the form x times s equal to q times z mod q, where this q is a public matrix and vector z is a binary secret vector. Okay, so this look quite familiar, but actually the harder part is still ahead. Why? Because vector z is still quadratic. It still has some kind of quadratic nature because each of its entry is a product of a bit from matrix X and a bit coming from vector S. Second, the component bits also additionally satisfy all the relations. Okay, so now we go to the second step when we handle this vector Z. We will employ a divide and conquer strategy where we view the whole problem as a bunch of sub-problems, where for each sub-problem we aim to prove that a secret bit Z has the form Z equal to C1 times C2, while preserving the possibility of demonstrating that the component bits C1 and C2 satisfy all the equations. To this end, we will use a permuting technique that based on two bits. Okay, this is as follows. First, for every bit C, we denote by C the bit 1 minus C. Then for every two bits C1 and C2, we define a vector, an integer vector, binary vector of length 4 that we call extension of C1 and C2, whose entries are the following. First, C1 bar times C2 bar. Second, C1 bar times C2. Third, C1 times C2 bar. And fourth, C1 times C2. Okay, so now for every two bits, B1 and B2, we define a permutation called T of B1 and B2 that transform an integer vector of length 4 that we call V, whose entries are V00, V01, V10, and V11, to the vector whose entry are V, B1, B2, V, B1, B2 bar, then V, B1 bar, B2, and V, B1 bar, B2 bar. Okay, so why should we come up with some kind of artificial permutation? Okay, the final goal is to obtain an equivalence. Okay, for all of C1, all of the bits C1, C2, B1, B2, we have this equivalence. Vector V is the correct extension of the bits C1 and C2 if and only if the permutation T, B1, B2 of V is the correct extension of two bits C1 XOR B1 and C2 XOR B2. Okay, so how does it work? Let's look at, let's consider an example to see what's happening here. Suppose that C1 is 1 and C2 is 0. Then vector V, which is the extension of C1 and C2, would be the vector consisting of the entries 0 times 1, 0 times 0, 1 times 1, and 1 times 0, would be exactly vector 0, 0, 1, 0. Okay, so we look at the entries of this, and we denote by V00 is 0, V01 is equal to 0, V10 equal to 1, and V11 equal to 0. Now, let's consider the permutation. Suppose that we will permute with the two bits, B1 equal to 1 and B2 equal to 1. Then the permutic vector T B1 B2 of V will be the vector V11, V10, V01, and V00, which is the vector 0, 1, 0, 0 in this case. And it is exactly the extension of two bits, 0 and 1. And it is and 0 is exactly C1 XOR B1. And 1 is exactly C2 XOR B2. Okay, so how can we make it useful? Actually, this concept already gives us a solution to the sub-problem. To do this, we first extend this secret bit Z to vector V, which is the extension of C1 and C2, the two component bits. Then we permute this vector V with random bits B1 and B2, and give the verifier the permutic vector. Okay, so the verifier can check that the right-hand side of the equivalent holds, which should convince him that the left-hand side also holds, and which convince him that original bit Z must be well formed. Furthermore, the random bits B1, B2 here essentially act as kind of one-time bet that perfectly hide the value of C1 and C2 from the verifier's view. Okay. So secondly, we also have to prove that the same bit C1 and C2 satisfy all the equations. So to do this, we set up a similar mechanism at their other appearances and use the same one-time bet at all of the places. So that's the main idea. So once we have the solution to this sub-problem, then we can also obtain the solution for the whole problem. Okay, putting everything together, so our new Stern-like techniques allow us to handle the quadratic relations. And to instantiate our group, lattice-based group encryption, we use the following ingredients. For encryption, we use an anonymous CCA2CQ public key encryption that obtained from the ABB identity-based encryption via the CSK transformation. For signature, we use the signature scheme that will appear at the conference, and my colleague Fabrice will present it to you tomorrow. This signature scheme interacts well with zero-knowledge proof. And finally, combining with known Stern-like techniques for encryption and signatures, we obtain the zero-knowledge protocol that is required for the group encryption construction. And that's it. Thank you.
So unfortunately, we're quite late, so let's skip the question session and give people a chance to switch tracks. Thank you.
Okay.